J-HAT 塾
Here we are asked to simplify this expression out here. So we start out by looking at the parts of this expression. There's this, and then this second part, and finally the third part out here. So first, we want to simplify the parts. For example, this one, the square root of 27, we can simplify it as follows. So we can express 27 as the third power of 3. And so the square root of that would be as follows. So 3 cubed can be separated into 3 squared times 3. And then we can now separate the radical sign. So it's now the square root of this term times the square root of this term. So the square root of this term remains square root of 3. And on the other hand, the square root of 3 squared is 3. And so this term here simplifies to this. Now, the second part, this one, we're also going to simplify it right now. Okay, so first we distribute the square root of 2 into the terms. That is the distributive property of multiplication over addition. So square root of 2 times square root of 6, square root of 2 times square root of 2. We notice that this bit here at the end, this is just 2, right? Square root of 2 times square root of 2, you just get 2 in there. Now here in the first part, 6 can be factored into 2 and 3, and this 2 and 3, they are under the radical sign, so you can just separate them again, like square root of 2 times the square root of 3 in here. And now we see again, square root of 2 times square root of 2, you get just 2. And then the square root of 3 remains here. And so this term here simplifies into this. Finally, the third term here, we have 6 over the square root of 3. So what we can do here is we can multiply the numerator and the denominator by the same number because they will cancel. It will just be 1. But we have to choose the number such that there will be no radicals in the denominator. Okay, we want to eliminate the radical in the denominator because we do not know how to divide 6 by some radical. Okay, so we want to get rid of the radical. And there are several numbers you can use for that, but the easiest would just be the exact radical that we have here. That's the square root of 3. So you have square root of 3 in here, square root of 3 above. So if you multiply this term, it's just like multiplying by 1. But now we combine the denominators so that we don't have a radical anymore. It's just the 3 here. And on the numerator, we have 6 times the square root of 3 in there. Okay? And now you can see that 6 and 3 cancel. So 6 divided by 3 is 2, and the square root of 3 remains here. Now, we combine what we got in the first part, the second part, and this third part. And so this is the first part now, it's the second part and the third part. And we immediately notice that this bit here, that's minus 2 square root of 3, and this one here plus 2 square root of 3, they cancel because it's a minus and a plus. And so what we're left is the first term here minus this term here. And so this will be our final answer.
J-HAT 塾
Now we want to express this expression here such that we can find the domain of X. So we just want an expression, an inequality where we know what are the possible values of X for this expression. So that's what we're looking for. And to do this, first we remove the absolute value signs. And to do that, all we do is we retain the expression here. So that's what we have here. And then we retain the inequality here. So that's what we have there. We retain this side, 7 over 2. And on the other side, we have this, and we just get the negative of this. Okay, so every time we have this kind of expression, to get rid of the absolute value symbol is you just copy whatever's inside the absolute value symbol. Then you attach the signs, the inequalities there. We've got less than in here. We've got less than in here. And then on the right side, you get the positive value of that. So that's what we have here. And on the left side, you put the negative value of that. Okay, so this is how you get rid of the absolute value symbol in an inequality. Now, this expression here is quite easy, right? All you need to do is you want to get rid of whatever this is, that's 3/2, okay, so that you can retain the x here. So to get rid of 3/2, you just add 3/2 to all sides of this inequality. So you add 3/2 here, you add 3/2 here, and if you add 3/2 in the middle, you get rid of the 3/2 here, so you only have x in here. Now on the left side, we notice that that becomes -7 plus 3, so that's -4/2. On the right side, that's 7 plus 3, that's 10/2. And if you reduce that to lowest terms, this is the inequality that you get. And so that's our answer here. Now, here I just try to graph it for you. The way we do this is first the absolute value expression. That's this blue one here. If you graph that, that's going to look like this. And 7/2 is this orange one here. Now the expression that we're looking at, the inequality says that the absolute value must be less than 7/2. So that means we're looking for the parts of this absolute value graph that is below the 7/2 line. And the 7/2 line is this bit here. So below that is this part, all right? This part. You see that part? And so because that's below the orange bit, that x, that set of x in that region where we shade gray, that's our solution. And that happens to be between x equals -2 and x equals 5. And that's exactly the same as what we got here in our answer.
J-HAT 塾
Now we are given this expression, and what we need to do is we want to factor this expression completely. Okay, so first we notice that this expression here, this is equation 20, expression 20, we can actually group it in the following, right? First part, we put the brackets there, and the second part here. But we notice that the first part, this is actually a perfect square trinomial. And so we express it as a square. That's x minus a squared. Now, we notice that this one is a difference of squares, okay? And we know that the factors of the difference of squares is such that it's the square root of the first term, so that's x minus a, minus the square root of the second term, that is just b. That's one factor, and the other factor is the square root of the first term, again, that's x minus a, plus the square root of the second term, again, that's b. So these are your factors. Now just get rid of the parentheses here. So we get this. Now, we can also write this one like this, because we notice that if we just put a negative sign, if we just multiply everything by -1 in the first expression, you get this one. And then if you multiply this one with -1, you just get this one. Since you multiply this one with -1, you multiply this one with -1. -1 times -1 is just 1. And so these two expressions, the one on top and the one on the bottom, they're just the same expressions. They're equal.
J-HAT 塾
Now for this problem, we are looking at two sets of numbers. The first set is this one and here. And we want to find the largest among it. And the second set is this one. And then we want to find the smallest among these numbers. Okay, so let's look at the first one. We just want the largest. So to do this, it is easiest to express each of these numbers in the same base. So let's look at the first term. The first term, okay, let's turn the radicals into exponents just because they're easier to deal with, okay? So first, this one is just 3 to the 1/3. That's good. Second one is just 9 to the 1/4. And the third one is 27 raised to the 1/7. Now, 9 can be, so the goal is to express all of them in the same base, because that way we can just compare the exponents. If they're all in the same base, then we just have to compare the exponents, okay? So 3 to the 1/3, it looks like 9 is just 3 squared and 27 is the 3 cubed. So we can use 3 as a common base here, but you can use other numbers if you want as your base, but I just find 3 to be the easiest in this case. So 3 to the 1/3, so that doesn't change. Second one, we express 9 as 3 squared. You got 1/4 outside, so 2 times 1/4, the exponent becomes 1/2, okay? 27 is 3 cubed. You've got 1/7 outside. 3 times 1/7, you got 3/7. Now, the bases are the same. We just have to compare the exponents. In this case, the base is 3, and 3 is greater than 1. When the base is greater than 1, then the larger the exponent, the larger the value of the entire number, okay? But this only applies when the base is greater than 1. For example, if the base is 1, the exponent doesn't even matter because it's just going to be 1 anyway, right? And if you have bases less than 1, then the greater the number in the exponent, the smaller the value of the entire number actually. In this case, 3 is greater than 1, and so we can just look at the exponents. And the biggest the exponent, the bigger the exponent, that's the bigger the value of that number. So you just have to compare these fractions in the exponent. First, we look at 1/3 and 1/2. So obviously, 1/2 is larger because the numerators are the same and the denominator is such that 2 is less than 3. And when that's the case, when the numerators are the same, the number with the smaller denominator is the bigger fraction. And so we can say that 1/2 is larger than 1/3. And then we look at 1/2 and 3/7. So 1/2 and 3/7, they don't have the same denominators. They don't have the same numerators. So the way we do that is we have to put them in the same denominator first, right? So the easiest way is just 3/7, 7 and 2, the least common divisor is 7 times 2, that is 14. So 3 times 2 is 6 over 14. 2 times 7 is 14. So on top is also 7. Okay, so we notice that 7 over 14 is larger, and so 1/2 is actually larger than 3/7. Now, just looking at these two inequalities, we know that 1/2 is larger than 1/3, and it's also larger than 3/7, and we're looking for the largest. And so the largest among these three is 1/2, clearly. But just for completeness, I also wrote that 1/3 is less than 3/7. Again, we do the same thing here. The least common divisor is 21, so that becomes 21. 1/3 becomes 7 over 21. And 3/7 becomes 7 over 21. Or sorry, 3 over 21. Clearly, sorry, that's 9 over 21 because there's a 3 there. 3 times 3 is 9. So clearly, 9 over 21 is larger than 3. That's 7 over 21. But again, you don't need a third inequality here. You just need the first two, okay? Because it says that the 1/3 is less than 1/2 and 3/7 is less than 1/2. Therefore, if you have all three of them, then 1/2 must be the biggest among them. And that's for the first part. Now for the second part, we have these numbers. We want the smallest among them. So let's look at 3. And again, we have the same strategy. Let's just put them all in the same base of the logarithm. Okay, so 3. And here we've got 3, and we've got here 9. So it looks like to me like 3 would be the easiest to deal with. You can use other numbers, but I think 3 is the easiest to work with in this case. Okay, so this one, 3. So how will you turn this into a logarithm? Well, you have a logarithm of base 3 and 3 to the third. Because in this case, if you do this, the logarithm here and the base here, they cancel, right? So they're the same. And so you're left with 3. And so 3 is equal to the log to the base 3 of 3 cubed. Okay, but we want that log base 3, okay? That's what we want because we want to compare all of them with the same logarithmic base. So 3 cubed is 27, so we leave that there. Log 3 of 27, that's the first number. The second number, 2 log of 5 to the base 3. Now you just have a 2 here, but the base is already 3, so we don't have to manipulate the base anymore. But the 2 here, that's multiplied by the logarithm. What we can do there is we can put this inside the logarithm. And when you put that number inside the logarithm, that becomes an exponent. So that becomes 5 squared, and 5 squared is 25. That's what we have here. So this number here is equal to the log of 25 to the base 3. Then we look at the third number. It's on base 9. Okay. Before we change the base, let's just also put 3 inside the logarithm. That becomes 5 cubed, right? 3 becomes the cubed here. And so this is 125, or just leave it to 5 cubed. Now, we can now change the basis because this is 9. We want 3. So the way we do this is we just get the log of the argument here. So that's a log of 5 cubed divided by the log of whatever the base here is. That's 9. So log of 9. And then we can put whatever base we want here. As long as it's not, it's positive and it's not equal to 1. Okay. So in this case, 3. So 3 is fine. It's positive. It's not equal to 1. So now that the bases are the same, we also notice that the denominator here, actually 9 is 3 squared. So log of 3 squared to the base 3 is just 2, right? This one cancels with the base here. So we're left with 2 in here. And 2 is like 1/2 in here, right? It's like a 1/2 coefficient. And so we can put that inside the logarithm again. That becomes an exponent. And so 3 times the exponent, that is 1/2, so 3/2. So this is our third number. Now we look at these 3 terms and you notice that they have the same base. So I'm just going to delete some of these bits here just so they're clear. So what we notice is that they all have the same basis now. That's the base 3 for the logarithm. And again, because 3 is greater than 1, all we need to do is look at the argument. And the larger the argument, the larger the logarithm, the larger the entire number is, okay? So we just have to choose, because here we're looking for the smallest among the numbers. So just have to choose which one is the smallest, 27, 25, or 5 to the 3/2. So clearly 25 is less than 27. But 5 to the 3/2, 3/2 is less than 2. And so 5 to the 3/2 is less than 5 squared. But notice that 5 squared is actually 25, right? So we can now say that 5 to the 3/2 is less than 25, which is of course less than 27. And 27 corresponds to this first number. 25 corresponds to the second number. And 5 to the 3/2 corresponds to the 3 or the third number. And so that means that the third number is actually the smallest, right? This is the smallest. And so our largest number for the first set is this one, and our smallest for the second set is this one.
J-HAT 塾。
We are given this quadratic equation, x squared minus 3x plus b equals 0. We are told that the solutions to this equation are alpha and beta. We're also told the following relationship between alpha and beta. It's such that the square of alpha plus the square of beta gives 1, okay? If you add these squares, you get 1. Now the question is, what is the value of alpha plus beta? So here we're given a squared plus b squared. Here we're asked a plus b, or rather alpha plus beta. And we are also asked, what is the value of b in here? So first is alpha plus beta. This is the sum of roots. And this is quite straightforward because we know that if you have this quadratic equation, ax squared plus bx plus c equals 0, then the sum of the roots of this quadratic equation, the sum of the solutions, can be obtained by just dividing the second term's coefficient, that's b, divided by the coefficient of the x squared term, which is a, and then you put a negative sign in there. Okay, so that will give us the sum of a, or rather alpha and beta. And in our given, b is, well, that's the coefficient of the x term, and we know that is -3. Okay, and a is just the coefficient of the x squared term, that's 1. And so we plug in a negative in there. So that's negative -3 over 1. And that just gives us 3. And so we know that the sum that we're looking for is just 3. Okay, so alpha plus beta is 3. Now, we want to look for the p, the constant term p. Okay, to find the constant term, we also use the following relationship. We know that this term here, the constant term, which is the c in here, if we have c and we have a, if we divide c by a, what we get is the product of the roots. Okay, so we know that the constant term divided by, that's the constant term divided by the coefficient of the x squared term, that's alpha times beta, because alpha and beta are the roots. Now, c in our problem is just this term here, which is p. So replace that with p, and a is just the item here, the coefficient of the x squared term, and that's 1. Okay, so we are told that in here, we are told here, where's that? Okay, we are told here that this ratio, this quotient is just the product of the roots, which is alpha times beta. And so we know that p must be alpha times beta. Okay, we got it from here, equals this, and then now we have this. Now, what can we do to find just p? Because alpha times beta, that's not really what we're looking for. We're looking for the actual number, p. Notice that we have alpha plus beta. So if we start from alpha plus beta equals 3, if we square both sides of that like this, okay? So on the left side, we get a squared plus 2, or alpha squared plus 2 alpha times beta plus b squared. On the right side, we got 9. We get 9. Notice that a squared plus b squared can now be grouped together here, and 2 alpha beta can be grouped together in here, okay? But alpha squared plus beta squared, we know that to be 1, okay? So we can just replace that with 1 there, right? And alpha times beta, we know that from here. That's just p. That's what we're looking for. So we replace that with p. So we are left with this equation here, which is easily solved, right? We just move the 1 to the other side and divide by 2. We get p equals 4. And so we know that alpha plus beta is 3, and we know that p is 4.